In the early 1990s, the engineers building the Internet realized their architecture was hurtling toward a hard physical limit. The network was expanding exponentially, but the underlying numbering system was about to run out of space. The constraint is embedded in the math of IPv4. It relies on a 32-bit address space, which means the absolute maximum number of public IP addresses available for the entire globe is roughly 4.3 billion. Every connected device requires one. To buy time, RFC 1918 carved out 3 specific blocks, the Class A, B, and C private IP ranges. These free internal addresses are strictly non-routable. If a packet with a private 192.168 IP tries crossing the Internet, the backbone router instantly rejects it. Because private IPs cannot survive on the open web, local networks cannot connect directly. Every piece of data leaving a private office network must pass through a physical translation mechanism first. That translation occurs at the border router. This piece of hardware stands exactly at the perimeter, keeping the isolated private local area network separated from the public wide area network. Running on this router is a software proxy called NAT, or Network Address Translation. Its job is to intercept outgoing packets and swap the non-routable private IP for a valid public IP. For NAT to execute this swap, the router requires strict spatial awareness. The network engineer must explicitly configure the interfaces, permanently designating one physical port as facing the inside private network and the other as facing the outside internet. When you observe NAT in action, you are not looking at a simple label swap. The router strips the packet header, rewrites the source address in RAM, recalculates the checksum, and pushes it to the WAN. To trace a packet through a modern enterprise topology, a network engineer has to understand how this translation logic evolved through 3 specific stages. The first stage is designed for inbound traffic. If a company runs an internal web server with a private IP of 192.168.1.10, clients on the Internet have no way to reach it directly. The direct solution is called static NAT. The network administrator takes a single public IP address purchased from the ISP and maps it strictly and permanently to that single private server. In a Cisco environment, this requires a specific global command, IP NAT inside source static. You declare the private inside local address first, followed by the dedicated inside global public address. When an external client aims a request at that public IP, the border router intercepts it, consults its mapping, and immediately translates the destination header to point to the private server. By typing Show IP NAT Translations, we observe how the router stores this. This grid shows a direct one-to-one link without port numbers. Its defining characteristic is permanence. Even if 0 traffic flows, this static entry stays permanently locked in the routing table. Static NAT perfectly secures external access to a single server. But if you have an office of 500 employees trying to reach the Internet, dedicating a permanent public IP to every single desktop is a mathematical impossibility. To get entire offices online, administrators adopted a secondary configuration, dynamic NAT. Instead of permanent assignments, it handles outbound requests on the fly. The engineer writes an access control list outlining which internal subnets are allowed to communicate externally. Then, they configure the router with an IP pool, a small batch of public addresses bought from the internet provider. Allocation is first come, first served. A user opens a browser, the router binds a free public address from the pool to that PC for the session. This exposes a bottleneck. With 10 public IPs, only 10 machines navigate simultaneously. The 11th machine is completely blocked. Dynamic NAT still consumes 1 public address per active user. To truly scale internal networks, engineers had to abandon one-to-one IP mapping and move further up the OSI model to intervene at layer 4. The solution is port address translation, universally known in Cisco environments as NAT overload. This is the mechanism running inside virtually every enterprise firewall and home router today. PAT stops relying entirely on layer 3 IP addresses. Instead, it lets thousands of devices share one public IP by hijacking layer 4 TCP and UDP port numbers to track distinct sessions. PC A and B connect simultaneously, generating identical source ports, 1054. The router processes PC A, keeping port 1054. For PC B, reusing 1054 would corrupt the return path. the router actively intervenes, hijacking the header to stamp a unique port, like 1055. Now, the return path is perfectly clean. When the data comes back from the internet, the router checks the destination port. If it says 1054, it forwards the packet to PCA. If it says 1055, it goes to PCB. This multiplexing happens millions of times a second. For a network administrator looking at the command line, it completely changes how the translation table reads. This PAT translation table explicitly dictates the transport protocol, TCP or UDP, and uses a colon to append the hijacked port number directly onto the global IP. This level of manipulation demands heavy processing resources. For every single packet passing through, the router's CPU has to open the layer 3 header, open the layer 4 header, alter the data, and recalculate both checksums to prevent the packet from being flagged as corrupted. The technique also completely eliminates end-to-end traceability. If you analyze traffic hitting an external web server from a massive corporation, the external firewall doesn't see 5,000 distinct machines. It sees a solid, opaque wall of requests originating from a single public IP. By hiding entire networks behind single addresses, Pat provided the critical breathing room needed to delay IPv4 exhaustion by decades. However, this fix comes at a cost. It breaks the routing principle that every internet device should have a unique, directly reachable identity. Today, NAT's role has expanded beyond IP conservation. Modern data centers and mobile networks are deployed entirely in IPv6 to avoid limits, yet they still must connect to legacy servers running exclusively on IPv4. These two protocols are mathematically incompatible. An IPv6 host has absolutely no mechanism in its networking stack to read, process, or route an IPv4 packet. To bridge this protocol divide, architects rely on a highly specialized translation mechanism called stateful NAT64. In NAT64's prefix embedding, an IPv6 client appends a 32-bit IPv4 address onto a 96-bit IPv6 prefix. When it hits the border router, the hardware strips away the IPv6 header, extracts the legacy address, and constructs a completely new IPv4 header from scratch. From there, the router simply applies standard NAT overload, stamping a port number and pushing the forged IPv4 packet out onto the legacy internet. NAT has evolved into a mandatory protocol forge, translating incompatible packets to maintain connectivity across a fractured global internet. To maintain these translations without dropping connections, the router has to track 4 distinct pieces of spatial information for every session. Cisco codified this into a specific 4-quadrant lexicon. This matrix maps the router's exact perspective. The first quadrant is the inside local address. This is the actual private IP assigned to a piece of equipment living entirely within your protected internal network. Next is the inside global address. This is the public IP that the border router uses to represent that internal machine to the outside world. The outside local address describes the IP of an external server, exactly as it is perceived by the machine sitting on your internal network. Finally, the outside global address is the actual physical IP, permanently assigned to that target server out on the public internet. These 4 quadrants dictate the router's entire spatial awareness. If an engineer understands where an IP falls in this matrix, they know exactly how the source and destination headers must be rewritten in both directions. The seamless connectivity users experience every day relies entirely on this mechanism. It is a carefully managed illusion, constructed, mapped, and executed millions of times a second entirely within the border router's RAM. Tracing a packet across a modern network boundary requires accepting that IP headers are not fixed coordinates. They are temporary labels, constantly erased and rewritten through Layer 3 IP manipulation and Layer 4 port hijacking. Success in complex troubleshooting comes down to interpreting that raw translation table, understanding exactly how the router rewrites reality to keep the data flowing.